Hi guys, welcome to the lecture on intermolecular forces and a brief discussion on crystalline solid structures. First, we're going to talk about intermolecular forces. The state of a substance, whether something is solid, liquid, or gas, is actually determined by the strength of intermolecular forces, or the forces that are between the molecules. So the stronger the intermolecular forces, those substances are going to be found usually as in liquids or solids. They're going to have high melting points and high boiling points because it's going to take a lot of energy in order to overcome the forces that are holding those molecules together. Weak intermolecular forces are usually substances with those will usually be found as gas states with low melting points and low boiling points. Because it doesn't take much energy to overcome the forces between those molecules. So there's four different types of intermolecular forces. We have dispersion, we've got dipole-dipole, hydrogen bond, which is not actually a bond, but we'll get there, and then the ion dipole force. So these are the four that we are going to concentrate on. Dispersion force, dipole-dipole, hydrogen bond, and ion dipole. All right, so let's take a look. Oh, first, you can see that as we go from left to right, we're going to increase the strength of the forces. So these guys, the dispersion are the weakest, and the ion dipole is the strongest. All right, so let's take a look at each in their own section. We will start with the weakest. This is called dispersion force, otherwise known as London dispersion force, or you may have heard of van der Waals forces, or any of those. It kind of all means the same thing. This is the default intermolecular force that is present in all molecules and atoms. So whatever kind of substance you have is going to have these dispersion forces. Even if it has other forces along with it. So this is kind of the default present in every single type of molecule out there. All right, so this dispersion force is caused by fluctuations in the electron distribution within molecules or atoms. So in electrons in the atoms or a molecule may at any one instant be unevenly distributed. So what that means is that, say you're looking at this ion cloud here, right, for particular, for example, iodine atoms. So there's two atoms here. We can see that in the right side, the electron cloud, that blue haze is the electron cloud, and we can see that there's more electrons in this instant towards the right-hand iodine atom than the left-hand iodine atom. You can see the left-hand iodine atom has hardly any electrons around it. So we can say that at this one instance, they are very much unevenly distributed. Well, that's going to lead to a slight negative and slight positive sides of these molecules. Not intentional, not full charges, just slightly. So the side that has more of the electrons at this instant is going to become slightly negative, and the side that has less electrons, all right, it's going to become slightly positive, because remember, those electrons are negatively charged. So if you've got more electrons around one side than the other, then it's going to be a slight negative charge. And if you've got less electrons than usual, then you're going to have a slight positive charge. And these are very instantaneous types of forces or charges. So it's going to happen kind of real quick. In fact, okay, we call this an instantaneous or temporary dipole because, again, this is just a 1 second, even millisecond kind of lapse. Over time, you're going to get electrons jumping from side to side in a molecule or atom all the time. So it's very transient. This instantaneous dipole induces or creates an instantaneous dipole in its neighbors too. So for example, if so it's kind of like they control each other's, I guess, charges in essence. So for example, if one electron has a slightly positive charge on one end, well, it's going to attract a slightly negative charge on a different molecule. So it'll, probably, push those electrons away from in the other molecule. It's kind of weird to think about, but in any case, they can create an instantaneous dipole in their neighbors as well. So the magnitude of force of these, very weak dispersion force, intermolecular forces, depends on the size of the electron cloud. All right, so dispersion increases with increasing size of electron clouds. So the larger the molar mass, all right, the larger the dispersion force. Okay, so the stronger it is. Even though they're super weak, the heavier that you get, the bigger the electron clouds, the stronger the attraction they're going to have to each other. So they're going to, it's going to kind of vary and range from super, super weak to, a little stronger than weak. All right. So that is the dispersion force. Again, it's present in every single type of molecule or atom, and it has to do with instantaneous dipoles of the electron clouds. All right, and are going to increase the size or the magnitude of this dispersion force is going to increase with electron cloud size. So here's a type of question that you may be asked knowing the knowledge that I just told you. So which halogen, chlorine, or iodine has the higher boiling point? Well, we got to think about what that means, right? High boiling point is going to indicate a strong or high intermolecular force. Okay, so we just talked about the dispersion forces. Dispersion force is going to increase with increasing molar or atomic mass, right? Increasing mass. So we gotta figure out which one is heavier, has more electron clouds, chlorine or iodine. If you look on your periodic table, iodine is below chlorine, so iodine has one more shell of electrons. And so that extra shell of electrons is going to create stronger dispersion forces. And so going to have a slightly higher boiling point. So in this case, iodine has a slightly higher boiling point than chlorine. So this is one kind of practical question that we can answer with the knowledge that I just gave you about intermolecular forces and in particular dispersion forces. All right, so dispersion forces were the weakest. The second weakest, or kind of going up in strength, we can say, is the dipole-dipole force. So this exists in all polar molecules. So we talked about polarity and shape a couple of weeks ago, and so we know how to find the difference in electronegativities between atoms in a molecule to figure out if it's polar or nonpolar. So this dipole-dipole force exists in all polar molecules. All right, and these are permanent dipoles. That means it's not instantaneous with the of the electrons jumping around in the electron clouds. But remember, in polar molecules, we have clear positive sides of the molecule and clear negative sides of the molecule because we have an unequal sharing of electrons. Okay, so this is that's the difference between an instantaneous versus a permanent dipole. So in molecules that are polar and have permanent dipoles, the positive ends of one permanent dipole attract the negative ends of another. And so you're going to get, an electrostatic force there holding those molecules together. Okay, it's not a bond holding atoms together to make a molecule. It is between molecules, and it's just a force of attraction. All right, so polar molecules have higher melting and boiling points than nonpolar molecules of similar molar mass. So as previous said with the dispersion forces are dependent on mass. Dipole-dipole forces are not dependent on mass too much. As much. So what that means is that polar molecules are going to have higher melting and boiling points than nonpolar molecules, because polar molecules are going to be sticking to each other through that force of attraction between dipoles. Nonpolar molecules do not have those permanent dipoles. They have very, very weak instantaneous dipoles. So they're going to have much lower melting and boiling points because it doesn't take much energy to overcome those forces. So we can see here, this slide has gone a little ghetto. We have polar and non-polar. All right, and we can see that these two molecules are of similar molar mass. So CH2O is 30 grams per mole, and C2H6 is about 30 grams per mole. But we can see that the CH2O's got an O here, which is very electronegative, and so that's going to make it polar. Okay, polar. And C2H6 does not have any strong electronegative atoms, so that is going to be nonpolar. However, if you look at the boiling and melting points for these guys, we can see that the boiling points, okay, and the melting points are much higher in number for the polar one, CH2O, than for the nonpolar one. And remember, look, these guys, they're negative numbers. So the smaller the negative number, obviously the higher the actual value. So for example, for boiling point for CH2O, it is negative 19.5 degrees Celsius, which is much higher than negative 88 degrees Celsius. Okay, and again, this all has to do with the dipole-dipole forces that are found in polar molecules and not nonpolar molecules. All right, so if we're talking about polarity and dipole-dipole intermolecular forces, let's talk about miscibility, which is the ability of a liquid to mix with other liquids. And if you remember from general chemistry, this has to do with the like dissolves like rule. In polar molecules, which have permanent dipoles, permanent positive and negative ends of a molecule, they can attract other negative and positive ends of a different molecule, no matter what type of molecule it is. It doesn't matter. So that means that polar liquids can mix with other polar liquids. Doesn't matter what kind, they can mix together. However, polar liquids cannot mix with nonpolar liquids. Why? Because nonpolar liquids don't have that permanent dipoles. They have instantaneous dipoles. So they may, be attracted for a second and then release, okay? Because they're not going to last. All right, so polar liquids and nonpolar liquids will not mix. The polar liquids will find each other and stick together, and the nonpolar liquids will just basically be kicked out and separated from those polar molecules that are all stuck together. So they don't mix. So this is a classic example of oil, yikes, and water. Okay, oil being nonpolar, water being polar. Here's a picture here. You can see that all of the water is basically clumping together, which kicks out all of the oil so that the oil can clump together. All right, so again, this is our like dissolves like rule. All right, so here's another sample question for us to solve with the information that we were just given. Determine whether each molecule has dipole-dipole forces. Now remember, we just said in dipole-dipole forces, they have to be polar. Okay, so the molecules have to be polar. So the first thing we have to do is figure out if these molecules are polar. All right, so CO2. Okay, so we have our C and our oxygens. Okay, I'm going to kind of skip to the structural formulas. And we know that oxygen is very electronegative, so oxygen will be pulling with electrons to either side. And remember, if we have equal and opposite pulling, these guys are going to cancel, and we're going to end up with non-polar molecule. All right, so if this is a non-polar molecule, it does not have a dipole-dipole force. The only intermolecular force that is in that would be the dispersion force, okay, where when we've got instantaneous dipoles being set up with slight charges for, a second or less. Okay, so let's take a look at the next one. CH2Cl2. All right, so H2Cl2. So set up something like this. All right, so we know that H and C's, if we look at the electronegativity difference, there is not, pretty much it's nonpolar. Okay, so the bond between C and H is nonpolar, but the bond between carbon and chlorine is definitely polar. So the chlorines are definitely more pulling with more force on those electrons than carbon. So we're going to have a negative, okay, side over here and a positive side here. So this means that this one is polar. It's a polar molecule. If it is a polar molecule, then it automatically is a is molecules, a bunch of CH2Cl2s together are going to have an intermolecular force of a dipole-dipole. So we can circle that and say, yes, this one has dipole-dipole forces. The last one is CH4. All right, so C with 4 H's. Again, when you look at the electronegativity differences between carbon and hydrogen, it's nonpolar. It's less than 0.4. So in this case, if they're all nonpolar bonds, it's going to be nonpolar. If it's nonpolar, it does not have dipole-dipole forces. Okay, so the only way to answer these types of questions is to go back to your knowledge of Lewis dot structures, structural formulas, electronegativities, dipole arrows, okay, canceling and whatnot. So you got to kind of combine all that information together in order to answer whether this is going to have dipole forces or not. Okay, so getting a little stronger as we go up the ladder of intermolecular forces. The next one we're going to talk about is hydrogen bonding. And I hate the name of this because it is not a bond. Okay, a bond is a interaction of the electrons of atoms to hold atoms together into a molecule. This is not a bond. All right, it is just a force between molecules, so it's not actually a bond. All right, so this is similar to the dipole-dipole because it has to occur in polar molecules, but this is special. The polar molecules have to have a hydrogen atom that is directly bonded to FO or N. So if the hydrogen is directly bonded to an N, an O, or an F, okay, like that, then it's a bit stronger because what do F, O, and N have in common? They are the most electronegative atoms on our periodic table. So they're going to be pulling electrons extremely hard. And so that's going to set up an even stronger a charge basically in the molecule. The F, the O, and the N are going to be, definitely negatively charged, where the H's are going to be definitely positively charged, even a little bit more than all of those other pretty strong negatively or electronegative atoms. All right, so we call this basically it's a hydrogen bonding intermolecular force, but basically, when it comes down to it, it is a super dipole force. Okay, it's just a dipole force on steroids. It is super dipole force. The large electronegativity differences and the small sizes of the atoms, okay, give a strong attraction between hydrogen in one molecule and the F, O, or N in the neighbor. But again, it is not a chemical bond. Okay, we said this before. Chemical bonds occur between atoms within a molecule. All right, and chemical bonds are much stronger than hydrogen bonds. Hydrogen bonds are going to occur between molecules. So here is a picture of a bunch of water molecules all together. All right, the chemical bonds are found between O and H. Okay, these white lines here, those are the chemical bonds. The hydrogen bonds in water is between the water molecules. Okay, this attraction between a hydrogen in one molecule and an oxygen in another. That is what we call a hydrogen bond. All right, so because we're talking about hydrogen bonding, which is stronger than the other two intermolecular forces we've discussed so far, because we've got a stronger strength of attraction between molecules, hydrogen bonding, again, is going to have much higher melting and boiling points, okay? In fact, it's going to be much higher than what you might predict based on molar mass. So here we've got two examples. We've got methanol and we've got ethane. They both have similar molar masses. However, check out their boiling points and melting points. Okay. Ethane is nonpolar. Okay, it doesn't have any dipole-dipole or hydrogen bonding intermolecular forces. The only thing it has is those very, very, very weak dispersion forces. On the other hand, methanol has this oxygen, which makes it polar. Okay. So polar, in fact, this oxygen is hooked up to the hydrogen, so that means we're going to have hydrogen bonding intermolecular forces, which are even stronger than dipole-dipole, and check out what happens when you have that really, really great increase in intermolecular forces. For ethane, I should say, for ethane, the boiling point is negative 88 degrees Celsius, all right, which is, really, I mean, at room temperature, it's a gas, right? Because the boiling point is, way below zero. However, if you have methanol, okay, its boiling point is 64.7 degrees Celsius, which is, basically just under what water boils at. So you actually, at room temperature is like, 20 something. All right, so at room temperature, this is going to be a liquid. It's not going to be a gas like ethane because of those intermolecular forces and those hydrogen bonds holding the methanol molecules together as a liquid. Okay, and the same with melting points. We can see that because it's polar and it has hydrogen bonding, it's going to melt at a much, much higher temperature than ethane. Okay, so keep that in mind. All right, hydrogen bonding is super important in biological molecules. If you have taken AP Bio or are in AP Bio, or if just remember biology from when you took it before, it's basically how the two halves of DNA are held together. Okay, those nitrogen bases, okay, the A's, the C's, the G's, and the T's are held together via hydrogen bonds, okay? Because remember, those bases are nitrogenous. They've got lots of nitrogen in them. And to be a hydrogen bond, it has to have a hydrogen hooked up with F, O, or N. Here's our N, okay? So we have a bunch of hydrogens hooked up with nitrogens, and they're going to be attracted, again, to each other. Okay, so it holds those DNA halves together. All right, so let's put our knowledge to some critical thinking. Which one of these compounds is a liquid at room temperature? Okay, so one of them is a liquid, so we can assume perhaps that the other two are going to be gases. All right, so let's take a look and see. We know that whether it's a solid, liquid, or gas is going to depend on the intermolecular forces holding it together. So let's investigate the intermolecular forces for these three compounds. So the first one we have is CH3F. Okay, so CH3F. All right, we know that between C and H, those are nonpolar. Fluorine is very much an electronegative atom, so it's going to pull on the electrons between carbon and fluorine towards fluorine. And so we're going to get a negative charge on fluorine, positive charge over here. So this is definitely polar. All right. So remember, two intermolecular forces can act in polar molecules, either dipole-dipole or hydrogen bonding. Hydrogen bonding must have hydrogens that are directly attached to an F, O, or N. In this case, we do have hydrogens, but they are not directly attached to F. They are attached to C. Okay, so in this case, this must be dipole-dipole. Okay, dipole-dipole bond. All right, so let's see, let's investigate the other ones before we can figure out which one is actually a liquid. All right, next we have H2O2. All right, hydrogen peroxide. So again, here we've got H's and O's. The electronegativity difference between H's and O's is very strong. We're going to have oxygen be pulling, okay, on these electrons more. It's not going to share fairly. It's going to be polar. And so we're going to have basically a negative charge towards the middle of the molecule and positive little ends here. Okay. So again, this is a polar molecule. Now we got to figure out which intermolecular force is applied in this polar molecule. Well, dipole-dipole, or the hydrogen bond that has to have a hydrogen directly connected to a hydrogen directly connected to F, O, or N. In this case, this hydrogen is definitely connected, both of them are connected directly to an O. So this is what we call a hydrogen bond. Okay, so if we had another H2O2 molecule hanging around, the H's here would be attracted, okay, to basically the oxygens, okay, of another molecule, and it's gonna be a lot more attracted than the CH3F over on the left side. Okay, last but not least, we have to take a look at the last one. All right, this is CH2O. Again, oxygen is much more electronegative than carbon. Okay, these guys are non-polar bonds. And so we're going to have a negative here, a positive on this end. All right, so again, it is polar. So is it dipole-dipole or is it hydrogen bond? Well, we've got hydrogens, but they are not directly connected to that O. So this is just going to be dipole-dipole. So if 2 out of the 3 are dipole-dipole and one of them is stronger in a hydrogen bond, and only one of these compounds can be a liquid at room temperature, it's got to be, which one? That's right, it's got to be this guy. Okay, this middle guy, H2O2. Because he's going to have stronger intermolecular forces. They're going to hold those molecules together in a liquid rather than being free as a gas. All right, so a lot of these questions have to make you think, okay? Make you think and reference what you know about, polarity and electronegativity and all that stuff to figure out why things work the way they do. All right, so we have come to the last, the strongest, the ion dipole force. This intermolecular force is going to occur in mixtures where we have ionic compounds and polar compounds. So for example, salt water, NaCl mixed with H2O. NaCl is our ionic compound, and water is our polar compound. All right, so this guy's polar, and this guy is ionic. Woo! All right, so when you mix NaCl and water together, the positive sodium and the negative chlorine ions are going to interact with water via ion dipole forces. This is, again, is the strongest of all intermolecular forces. So let's take a look at how this works. In this intermolecular force, it's kind of weird that we call it a real intermolecular force, because when you mix salt into water, the salt is going to dissociate into ions. Okay, and so the chlorine ions are going to be attracted to all of the hydrogen molecules, okay, in the water. So we're going to get a bunch of hydrogens attracted here. Okay, so the hydrogen is going to be closest to the chlorine because hydrogens are, going to be positive and chlorine's negative. On the other hand, we've got sodium that is also dissolved in water, and so a sodium ion is positive, so it's going to be attracting the oxygen ends of the water molecule. And so we're going to get basically little sodium or chlorine ions that are surrounded, like little, with little bubbles of, not literally bubbles, but little beads of water fully surrounding them. Okay, and so this is be the strongest of all intermolecular forces. They, hold real tight. All right. So this is what we call an ion dipole force. Again, only happens when we mix ionic compounds with polar compounds. And, most of the time the examples will be, an ionic salt that's been dissolved in water or some other polar compound. All right, so here is a summary chart of the type of intermolecular force attractions, and what's involved, what occurs between them, the strength of attraction, and effect on boiling point. But as you can see, as long as you can recognize that as you go down from dispersion down to ion dipole, we are going to increase those boiling and melting points dramatically. Okay, so those ion dipole are going to have the highest boiling points versus the London dispersion. In fact, ion dipole is why we have what's called boiling point elevation when you mix anything with water, okay, especially salt. So say you're cooking a pot of spaghetti, and some people like to put in their boiling water some salt. Okay, they add salt. Why? It's going to increase the temperature at which the water boils at. Okay, because we got to break up this attraction between the water and those sodium and chlorine ions to even let the water evaporate. So it's going to definitely increase those melting and boiling points for sure. All right, so the last section of our notes is all about solids, okay, and crystal solids, for example. So there are several types of solids that form this crystalline type structure. So the first one we're going to talk about is molecular solids. And these guys are solids whose composite units are molecules. So these are going to be covalent compounds, basically. So these solids are going to form little crystals, but they're going to be covalent, okay, solids. So they'll be held together by dispersion forces, or perhaps dipole-dipole or hydrogen bonding. We're not going to see any ion dipole, because none of these are going to be ionic. So they're going to have low to moderately low melting points compared to the vast majority of the crystalline solids, because they're mostly going to be held together with the weaker intermolecular forces, right? So these guys are on the weaker end. So their melting points are going to be low to moderately low. So here are just a couple of examples of molecular solids. This is dry ice, CO2, okay, and this is water, apparently. Yep, water. Okay, so H2O, and so it's interesting to see the difference between how CO2, okay, is coming together to form a solid, okay, versus the spread apart H2O molecules, which kind of gives you the, remember that ice floats when it's solid. It's one of the only substances that actually does that because it decreases in density. Okay, so we can actually see that when we look at the crystalline structure of both of them. All right, another type of crystalline solid is, well, if the last one was basically covalent solids, these ones are ionic solids. And these guys are composed of units that are what we call formula units or ionic compounds. These guys can be held together by electrostatic attraction between the anions and cations, all right, that are making up the ionic solid. And they form what's called crystallattice structures, alternating cations and anions in a 3D array that keeps basically kind of everybody as happy as you can be, right? Where each of the negatives are as far apart from each other and as close to another positive, and all of the positives are as far apart from each other and as close to negatives surrounding it as possible. All right, so compared to our molecular solids, which were covalent, ionic solids are going to have much higher melting points and boiling points than molecular solids. Okay, so these guys are going to be melting at a much higher temperature than the, the molecular solids. In fact, you can think about it. Okay, so dry ice sublimes, goes straight from a solid to a gas at room temperature. Ice melts at room temperature. Those are both molecular solids. But if you take a crystal of salt at room temperature is still a solid because it hasn't reached a high enough temperature in order to melt yet. So these are going to be a lot of your solid crystal substances that we work with, table salt and all the other kinds of salts that are solids at room temperature. All right, so last type of crystalline structures, we had covalent, we had ionic, and now this is just plain old atomic. These are atomic solids. These are solids whose composite units are individual atoms. All right, they are not going to be bonded together. They are just kind of held together as a crystalline solid. So an example would be diamonds. Okay, diamonds are made of nothing but carbon atoms that are held together as a crystalline structure. Iron, xenon, okay, they've got different types. So basically there's 3 different categories for atomic solids. We can have covalent atomic solids that are held together by covalent bonds. These guys are very strong, high melting points. Okay, this is the diamond in effect. Okay. Then we have non-bonding atomic solids like xenon. Remember, xenon is a noble gas, so he's not actually going to be bonded to any of its neighbors, like chemically bonded to any of its neighbors, but he can be held together in a crystalline solid by weak dispersion forces. Okay, so this is going to have very, very low melting points. In fact, to even get non-bonding atoms to make a crystalline structure, you have to have extremely low temperatures and high pressures to do so. So this is xenon gas, right, in solid form. And again, this only occurs basically with really, really high pressure and really, really low temperature because you're going to have very low melting points. And the last category is the metallic atomic solids. This is like iron, all right. Basically looks like rocks. Rocks, we can call them crystalline type structures. These guys are held by metallic bonds, remember, because anything that's just pure metal atoms is going to be metallic bonds with a sea of electron, and they're going to have variable melting points. Okay, it just kind of depends on the strength and how those electrons are floating in that sea. All right, so that is what we call atomic solids, made up of individual atoms, okay, and basically of one kind of atom. All right, so it's not going to be in diamonds. You're not going to find carbons with hydrogens or bonded to anything else. It's just a bunch of carbon atoms bonded together. Okay. All right, so we got atomic solids, which are pure, made up of purely one type of element. We've got molecular solids, which are made up of covalent compounds, and we've got ionic solids, which are made up of ionic compounds. All right, so let's use our knowledge to do some problem solving. Identify each solid as molecular, ionic, or atomic. All right, so this is as simple as taking out your periodic table and figuring out if something is made up of a single type of atom, in which case it's atomic. If it is made up of metal and nonmetal, in which case it's ionic, or whether it's made up of purely nonmetals, in which case it would be molecular. So if we take a look at CaCl2, Ca is a metal, Cl is a nonmetal, so this is ionic. The next one is cobalt. Cobalt, it's not attached to anything else, it's just cobalt, so this would be atomic. Cs2, both carbon and sulfur are nonmetals, so this would be molecular. The next one is NH3. Again, both nitrogen and hydrogen are nonmetals, so that's going to also be molecular. Next one is calcium and oxygen. Calcium is a metal, oxygen is a nonmetal, so that is an ionic bond. So that is also an ionic solid. And then last but not least, we have Kr, which is just krypton. All right, nothing more added, so this is going to be an atomic solid. All right, so those are pretty easy and straightforward. All right, we've got 2 more slides in this lecture, and they're going to be devoted to water because it is such a remarkable molecule. It is the most common and important liquid on Earth and for us. Okay, our bodies are made up of 75% water. So, water fills oceans, lakes, streams. It humidifies our air. Our majority of our body mass is water. Life is not possible without water. That's why there's this big hoopla with Mars, and they're finding supposedly water there. So they're like, oh, if we can find water, maybe we can find life. Okay, because life is not possible without water. All right. So water's got some unique chemical characteristics. It's super low in molar mass. Okay, water is 18.02 grams per mole. Yet it is a liquid at room temperature. Remember when we were talking about really low molar mass stuff? They're usually gases at room temperature, but water, no. Water is a liquid at room temperature, and it's because it's not dispersion. It's not held together by dispersion forces, but it goes, bumps up 2 levels to be held together with intermolecular forces of hydrogen bonds. All right. It's also got relatively high boiling point, okay, due to its molecular geometry and its polar bonds, like we were talking about. So it's going to take a lot of energy to boil it. And it forms strong hydrogen bonds with other water molecules. So it can dissolve other polar molecules and ionic compounds. So it's one of nature's, like, we call it a universal solvent, because it can dissolve almost anything. Okay, there's a lot more ionic and polar molecules or compounds in the world than nonpolar. So water is going to be able to dissolve and be a solvent for many different kinds of compounds. Speaking of, it is the main solvent of living organisms. Inside of your cells, okay, you've got water. And in that water is a bunch of salts and little tiny cell parts and all that stuff. It's going to help, water helps transport nutrients and other important compounds in and out of your cells and around your bodies and all of that. Okay, water helps to do all of that. It's very cool. And then, as I mentioned before, it expands upon freezing. Okay, ice is less dense than liquid water, so ice floats, which is super important. Okay, because if ice did not float, then when lakes and rivers and streams freeze over in the winter, basically it would sink to the bottom and destroy the plant life at the bottom, which destroys animal life as well. So it is a good thing that ice floats. It allows life to go on underneath its surface. Although there is one bad thing about ice expanding upon freezing, is that because it can expand on freezing, if any cells, hopefully not us, hopefully you're not thrown in the freezer, okay? But as an example, a lot of foods like that are made of plants and plant cells, like lettuce, okay? Here, here's a classic example. If you freeze lettuce, okay, slowly, it's going to allow the water to expand and burst, basically rupture the cells. All right, and then when you thaw it back, all of it's like limp as heck because all of those cells are basically ruptured and bleh. Okay, so that's why and if you love McDonald's, good for you. But every time I go to McDonald's, whether it's on my hamburger or a salad, and that's why I don't eat McDonald's anymore, the lettuce always looks clear, glassy, and limp because it's always been frozen and it's gross. So yes, my lettuce from McDonald's always looks like this and never like the fresh head that I get at the store. And it's because they have to freeze, the ingredients in order for them to last longer for transport and all that stuff. So it's going to rupture the cells and make it all bleh. All right, so one way to kind of get past that is what companies have figured out is if you flash freeze veggies and foods that have high water content, basically flash freeze is freezing them so quickly that water cannot expand as much as if you're letting it freeze over natural time. So water is frozen, but it doesn't get to fully go into its big crystalline, less dense structure. So it saves the cells. It doesn't rupture as many cells, and so you get a fresher taste after it thaws out. In any case, there you go. So that's our lecture about intermolecular forces, crystalline structures, and the remarkable molecule of water.